All right, so we're going to look at how we determine cut points. So we talk a lot about cut points in health, but cut points are not just limited to health, they are also limited to other things. Like, for example, how do they determine the cut points to get into West Point? It's a point-based system, and there must be some kind of science behind how they actually develop those cut points. And by the way, there's a beautiful RAND study about admissions data and success in the military, which is pretty interesting if you want to pick that one up. But the example I'm going to pick is blood pressure and type 2 diabetes. So if I wanted to use blood pressure, having high blood pressure is not a disease. Blood pressure is a screen for other diseases, and it's a screen for other diseases because taking blood pressure is easy. Determining whether you have type 2 diabetes requires a blood draw. So what is blood pressure? It actually consists of two numbers, systolic blood pressure and diastolic blood pressure. And it's displayed as a ratio, but it's not really a ratio. It's just two numbers. They could have actually done an ordered pair if you want to think of it that way. Systolic blood pressure is the pressure on your arteries when your heart is contracting. And diastolic blood pressure is the pressure on arteries between heartbeats. So the question is, if I'm using blood pressure as a proxy to tell you that you might be unhealthy, at what values of systolic blood pressure and diastolic blood pressure should I tell you it's time to get a blood draw? So to do this data analysis, I'm using the CDC's National Health and Nutrition Examination Survey, or NHANES for short. NHANES is a wonderful database with many things in it. I'm just using certain things related to blood pressure here, but it's gathered yearly by throughout the year by the CDC through mobile exam carts, and they go throughout the nation and they collect a representative sample of data nationally. There's nutrition data, there's blood pressure, there's actually a dual X-ray absorptiometry machine in each one of the mobile carts. That's DEXA for short. So the DEXA machine collects percent body fat, fat-free mass, head weight, leg weight. You can't imagine the data that's in this thing. Some of you have seen a little bit of that data, and it's pretty overwhelming. But what I'm interested in is that NHANES has actually directly measured SBP and DBP. They also they don't have blood draws, but they have self-reported answers to, have you ever been told by a doctor that you have diabetes? There's other questions related to diabetes in this database, but this is the one I focused in on. So you could answer yes, no, borderline, and they had some other numbers like refuse to answer or I don't know. And so I discarded those. And I took the yes to be, yes, you have diabetes, and borderline I also took as a yes. So I coded all the ones and threes as being 1 for having diabetes and all the 2s as 0, and I discarded any subjects that refused to answer or didn't have data or just didn't know. So I'm telling you this because part of data analysis does, especially NHANES is a very nice database actually, even though it might be overwhelming, but I still have to do some prep of that database. Doing that prep in R is actually fairly easy and nice, but I did it in Excel by just sorting, and when you do those things, you run the risk of actually corrupting your database. So hopefully I didn't do that. So I went to the SBP, the mean SBP. They take 3 readings, and the lowest out of the entire nation that was collected was 72. So what if I use 72 as a cut point? It's the lowest possible seen. Well, the problem with that is that everyone over 72 would get a blood draw according to my criteria. If I use the 72 as a cut point, it's the lowest value that's seen in the database, then everybody is considered at risk, and everybody would have to be sent for a blood draw. Well, that would be good because then I'd catch anybody that actually does have type 2 diabetes or a true positive. But the problem is you get a whole lot of individuals who'd be getting unnecessary blood draws because they don't need them because they never had diabetes. So this is probably not a good cut point. But just for the sake of this exercise, I'm going to take 72 as my cut point and show you that it's a bad cut point by using mathematics. So how do we do that? Well, the first step is I need some numbers. I need what's in my database is the total population. I've discarded some things, and I want to count the number of people that I've classified as actually having type 2 diabetes. And I'm also going to keep track of the disease-free as a debugging piece, that I know that things are supposed to total up in a certain way, and I'd like to know this number. So it turns out that the total population in my database was 27,635 individuals. Out of those, the number that got ones, the number that said that a physician had told them that they have type 2 diabetes, or the number that, that said they were borderline, they were 1,935 individuals. And then I just subtract the two to get the disease-free. The second step is I need to start counting how many individuals this particular cut point correctly identified and incorrectly identified as being at risk, as being diseased. So realize that I started out with 72. It's just an exercise, but it's a nice start because it'll show you where everything is coming from. So the first thing I need to count up is the true positives. Those are the people that I sent for a blood draw that actually did have the disease. So that was everybody, because I sent everybody to go get a blood draw. So that's all 1,935 of them. The false positives, unfortunately, are the people that I sent that I thought falsely classified as having the disease when they really didn't have it. And that's everybody who was disease-free. That would be the 25,700 individuals that didn't have type 2 diabetes, that because my cut point was too low, I sent them all to get blood draws anyways. So false negatives are the people that you falsely classified as being disease-free. Well, I sent everybody, so I don't have any false negatives. And the true negatives are the people that you truly classified as not having the disease. Well, I screwed that one up, so the true negatives I didn't get right at all, so I get a 0 here. So what's going to happen is, right now my cut point is 72. If I start raising that cut point, the false positives will start going down, because I'm going to stop incorrectly classifying people as having the disease when they didn't. And the false negatives will go up, because I'm going to somehow catch some people or fail to catch some people as I start raising that cut point. And the true negatives also will go up. So what I really desire to get a good cut point is I want to minimize my false negatives and maximize my true positives. So I do this by calculating rates. And these two numbers are called sensitivity and specificity. So someone in class asked about sensitivity analysis. That's something different. This is also called the true positive rate. So it's the rate that I am classifying true positives correctly. And in this case, I got everybody, so it's a 1. So this is formula. You can put it into code. Specificity is my true negative rate. And I really botched this one, so I get a 0. And the next step is to make the ordered pair. This number here is, you can think of it as the false negative rate. So this is the false negative rate, and this is the true positive rate. And what you would like to do is get this true positive rate as being as close to 1 as possible, while getting this number as close to 0 as possible. And so you can do that. That's actually calculus. So I'm not going to do this by hand unless I want to give myself a punishment, but I start raising my cut point, and then I redo this analysis, and I'll keep getting these ordered pairs, and I can graph these ordered pairs, and that is what we call the receiver operating characteristic curve. So now I'm going to show you an automated version of this, because I don't want to calculate these by hand, because there's, I think the highest value of cut point was 133 or something like that. So I don't want to do those by hand. So everybody watching this that uses R and Python will shudder a little bit, but what I did is I wrote code. I just took the NHANES spreadsheet that was given to me in Excel, and I was a little lazy. I just wrote code. If you want to see the code, all you have to do is click this guy here and right click it and click assign macro and look at edit, and it will allow you to see the code that's hidden behind if you push that button. And you can see those formulas, the calculation of the true positives, false negatives, and so forth. These are the sensitivity and 1 minus specificity. And so you can see all those things in there. But so I'm doing exactly what I did for 72, but I'm running a loop and having it automatically do it for me. And this is my, by the way, this highlighted row column is my generated, those people who I claim have diabetes are tagged as 1. I had it spit out my results in the output my results into the next spreadsheet. And this is diastolic. Let me show you the systolic one first. So this is systolic, and this is 1 minus specificity every time I get an ordered pair. Initially, I got 1 and 1. Recall that specificity was 0, so 1 minus 0 is 1. So I start right up here, and then as I start raising my cut point, what's going to happen is that the false negative rate is going to start going down because it's closer to 0, and the true positive rate also unfortunately will start going down. So I get this curve, this concave down looking curve, and that's called the ROC curve. And this point right here, where x is equal to 0, or the 1 minus specificity is equal to 0, and the sensitivity, which is the true positive rate, which is at 1, that would be the optimal point. You'd want to have as little possible as false negatives and as much as possible as true positives. So the point on the curve that's closest to being that point over there, or the closest in distance, would get me the optimal point. And I used calculus, but you can actually do a sort and find that manually. But what I did is I interpolated a curve, and that sounds like hi-fi, but all I did is I said trend line, give me a trend line, gives me a good R-squared and makes close fit. And I put that into something like Mathematica called Maple, just because it was there. And I calculated what's called the area under the curve, which is just the integral. The integral, the area under the curve, if I do a very good job, if this is a good diagnostic, I have to also evaluate the quality of what I'm doing. The area under the curve would be 1, because the best area under the curve would be I have just a horizontal line here. Unfortunately, hardly anything gets you that. So we get an area under the curve here of 0.73352, which is like academic grade, so it's like a C, just about a C. So that's actually pretty good in the world of medicine. So I'm happy with that. To find the minimal distance from the edge to the curve, I calculate the distance formula between the 0.01 and the curve. So x minus 0 quantity squared plus the y value is 1 minus the curve itself quantity squared, and then take the square root of that, calculate the derivative, and set the derivative equal to 0, and I get one real number here. That's 0.321 from the x-axis. If I go to the data points, the x-axis would be the column E. If I go to the data points and look for around 0.32 somewhere, and I go find the cut point that yielded that x value, I get the optimal cut point is 122. The American Heart Association has 120 as a cutoff as long as the systolic is, the diastolic is below 80, and it has 130 as the cutoff if the diastolic is over 80. So it has a decision tree cutoff point. But this is the systematic way to find that cutoff. I also ran the diastolic. That was the other one that I didn't show you guys in class. And it's actually horrible looking. This almost looks like I have drawn the y equals x line here, because y equals x, the area under y equals x is 50%. That's failing. And so this curve is very close to failing. And in fact, when I calculated the area under the curve, I got 0.56. That's a failing grade. It's definitely not something I would publish. The cut point I came up with in the same way that I did for the other one was 80. So the official cut point. And so that's actually the cutoff of normal blood pressure. So that's pretty interesting to me. So the numbers I'm coming up with for detecting type 2 diabetes is around 120 of systolic blood pressure and 80 for diastolic. The cutoff for diabetes that they have in their report is 130, and I can't remember the diastolic. But diastolic is not a good predictor or classifier. So this evaluates whether what you're doing makes sense. I could take anything, say, I'm going to count the number of freckles on your face and see what the relationship is to type 2 diabetes. What you're going to find is you're going to get a terrible looking ROC curve. Okay, so that's it.